that going. Okay, we're recording. All right.
Hey guys, how's it going? Bring that bell.
Now, I will say this. Just as a reminder, I am recording lectures and putting them up on my YouTube channel. Don't forget to subscribe. Now, yeah, it's on there. AP lectures, they're going to be there. Yeah. Today, yesterday we went through and we talked about bonds and these intermolecular forces, right? So, real quick, bonds. One thing about bonds is that those are whenever you have one molecule together, right? The forces within a single molecule, those intramolecular forces. And then the intermolecular forces, so when you have multiple molecules, how do they interact together? That's what these guys at the bottom are. Okay? So, what we're going to do today, this is going to be a little bit of free response practice. Okay? Now I'm going to say this. This isn't going to be graded. I'm going to go walk around and give critiques, but I'm not going to say oh, you're going to fail because of this, okay? I want you to just try, put whatever you think on there, and then I can go through and be like, actually, do this instead, okay? So, what I want you to do is, I'm going to give you a situation, and then you're going to draw a molecular representation of it, okay? So when I'm up here drawing out like hydrogen and how it's interacting with other things and so on and so forth, I want you to do that, okay? So you go through and do that, because guess what? You'll be required to on exams. And then you may want to go through and also throw in an explanation, so like a sentence or two about what it is that you're actually drawing, okay? Okay. So I'm going to even give you an even bigger hint. I'm going to go through and tell you what forces I'm expecting, right? At least say this is you can expect to draw and explain one type of bond. So it's going to be one of these bonds. Okay. I may say, here's a situation, draw and show the intermolecular forces. And I say forces, there's two of them. Ooh. So you have to show me the two intermolecular forces that are at play. Alright? Does that make sense? So let's start off with something a little bit easy. Alright? You also need to take into account things like, is this a solid, liquid, or gas? And show that. Okay. We're just going to try it. Like I said, right now, give it a shot, draw it down, get an actual, there's something about you actually writing something that gives it a bit of finality, locks in your answer. So definitely do that. Don't just think about it in your head, because it's really easy to think about it in your head and go, I kind of got it, and move on. Okay. You guys ready? Nope, I'm not ready. Smartboard's not ready, exactly. Alright, number one. Draw a molecular representation of a pile of sodium chloride.
You're right.
How about it? So we're doing free response practice. So I'm going to write a scenario on the board. You draw a molecular representation of it, and explain what bonds or forces are at play. While you guys do that, I'm going to check to make sure no one's missing exams or quizzes or anything like that, right? I think this class is pretty set. Although I will need to nothing yet? Think it over. Well, first off, one thing you might want to think about if you're kind of like lost. Okay. First off, think about sodium chloride. What type of bond is sodium chloride? Yeah. So now, draw an ionic bond. If I was drawing an ionic bond, what would I draw up there? Draw that. So go through and draw it. Go. Gets a nice clear shade of shade. Alright, I think it's going to be good enough. We're going to move slightly briskly. So, this is kind of how I would go about doing it. Let me make this a little bit larger for everyone. Something like this. Right? They're ordered, they're in a pattern, it has a positive, negative pattern. Remember that it's just, this is two-dimensional, but yes, you can go and do a three-dimensional thing this way as well, out of the board. Now, I've shown that this is a positive and a negative charge, right? It doesn't have that little squiggle symbol, little lowercase delta. So that doesn't mean it's not slight, it's a full-on charge, right? Okay? Do you see, I notice I didn't put little things in it. What does it mean if I have a little dash, a little line between two atoms? What does that mean? They're not bonded. Because this is ionic bonded, but I didn't show that. What does it mean whenever you have a line? Electrons are being shared. Does ionic bonds share electrons? No. So today is going to be a kind of cleaning up this stuff a little bit, right? So there's that. Yeah, and there you go. There's that.
That's it.
Yeah. I would go through and explain it as well. So how would you go about, let's go talk about the words part of this, okay? If I really wanted to go through and get a full-on explanation, right? You may have noticed that on these FRQs, sometimes I'm only wanting like 2 or 3 points. You know, if I wanted a full, as much as you can possibly tell me about this. These are some things that you might want to talk about. So one, that the electronegativity difference between sodium and chloride is high or low? The electronegativity difference.
Yeah.
Very high, right? Super high. One's way over here, one's way over there. Right? You could say that you have a metal and a non-metal, right? That's another way of saying it. So this is things that are leading you to, oh, this is an ionic bond. So if you have this large electronegativity difference, you have one thing that has lost an electron, giving you a full positive charge on that atom. One that has gained an electron, giving a full negative charge. The distance between these two charges are small, which leads to a very strong attractive force between the two. You might want to make a point saying that they do not share electrons. And then all of these things kind of are describing an ionic bond. All good? Okay. So this is, again, this is kind of free response practice thing. All right. Next thing. Should I jump in the deep end or go?
No.
Let's go deep end. A solution of sodium chloride in water.
Alright.
So draw that.
Yeah, now you regret your decision, huh? I have ideas.
So, like I said, today, here's the thing. Okay, I'll give you a hint, okay? You need, so sodium and chloride, tell me if you see bonds there. H2O, indicate what bonds are there. And then I'm going to even give you a bigger hint. There are two intermolecular forces at play. You need to see two of these guys.
Oh, okay.
I'm not going to tell you which ones. Those are the things I'm going to be looking for. What's going on with this bond? What type of bond is here? And indicate two different intermolecular forces. So while you guys do that, I'm going to tell you what me and some buddies of mine were talking about a couple nights ago. I was sitting around playing some video games with some old grad school buddies. They're all PhDs. They're off either teaching or doing industry work or research, something, all different stuff, right? And I was telling them about my class, kind of, what we're doing and whatnot. And they said, wow, my undergrads don't even do that. So, here's the thing, exactly, right? They complain all the time about their undergrads. Continually complain that their undergrads are awful, they don't know anything, they're not hard workers, they don't blah, 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 complain. And initially when I told them what you guys were doing, they were like, man, you push them pretty hard. And I'm like, yeah, do you want to keep complaining about your undergrads? Because I'm teaching your future undergrads. And they were like, okay, you can keep pushing them hard. Okay. I never want to see anyone in here be the guys that they're complaining about. So if I seem like I'm pushing you hard, maybe, but I also hear what's on the other side. So yeah. So yeah, whenever I give you two deep questions like this. That may be one. Alright. So we get that. So I'll say this. One thing you might want to think about. This is sharing electrons, right? What is this? That's an intermolecular force, right? It's an attraction. No electron sharing or anything like that. Just a little force like that. Okay. I'm gonna walk around and see what you guys say a million. I'd say maybe 6. I'd say about 6 H2Os. If you want to represent like 1 or 2 sodium and chloride. So, here's the thing. This looks like a solid. And here's the salt. So I'm going to say this. This is very, very comforting. Like on an exam, right? If I look at this, sometimes it's water, big, big. Yeah. But we're practicing.
Trust me.
We're practicing.
I'm gonna try harder.
No,
Great. So.
Yeah. This isn't for a grade, but I'm going to critique you as if this was an exam.
Just
Okay.
practice as you'll.
Make it, but bigger the better. Bigger the better. That way, because think about this. The readers, they grade about 100 or so things a day. So imagine someone grading 100 things. If they have to try to think about understanding what's going on, they might just go 0, move on. Okay? Make it as easy as possible for them to understand.
That's how I don't understand people who grade like the essays. That was
They enjoy it. That's one note. I'm gonna go through and say like, if this was, some of these pre-response questions are like out of two, right? Where you don't need to do everything completely. Let's go through and practice like everything is worth 30. Like make it as detailed as possible. Go through and I'm gonna be as pedantic and as critical as I can be. Okay. Not because I want to be a jerk, because I want to make sure we get it right. Okay. Looking pretty good. So let's go through and do this. So first off, we have a solution of sodium chloride in H2O. Okay. Now, do you guys remember what happens whenever a sodium and chloride get in water? What happens to the sodium and chloride? They separate out. So will it have an ionic bond? No. No ionic bond here. What about the bonds in H2O? They stay the same, right? But what type of bond is that? Covalent bond, polar, nonpolar? Polar. So, to satisfy this, you just have to not have an ionic bond. To satisfy this, show some kind of thing like this. Basically saying like, I'm drawing everything. But if you indicate this in any way, that there's more electrons here, that there's a negative charge here, and positive charge here, you draw the little arrow, something to indicate this is a polar bond. Even if you write polar, then that would get you some points there. Okay, that's why I like free response, man. You could do.
I like free response more than multiple choice. That's the one.
I'll say this. I find multiple choice to be easier, but I enjoy free responses.
See, I flipped it. I think, for some reason, I think
Okay.
that's closer.
So, we've gotten that. Now, the two intermolecular forces. What intermolecular forces do you think we have? Ion dipole
Hydrogen bonding.
and hydrogen bonding.
Yeah.
So, ion dipole, let's take care of that first. So let's take the sodium. Positive charge there. You have an interaction taking place between a dipole and an ion. So at this point you can draw a little arrow and say ion dipole force, right? You can go, you'll probably want to draw another water and show that the chlorine hydrogen force happening. If you want to go and continue on, is it just going to be one and one?
No.
No, it's going to be a bunch of them, right? You know, so on and so forth. You can take some time there. Additionally, what other forces are there? Yeah, we already said hydrogen bond. So then we want to go through and maybe draw a couple waters and show a hydrogen bond.
Here's what's happening with salt, and also H2O2
Yeah, exactly. I would say this, honestly, if someone said, draw the intermolecular forces involved in dissolving salt, I don't think that this is going to be on their mind, right? Water does what water does. But if they say, what is the intermolecular forces involved with water, liquid water, that's that. Or if they say this and say the words, all forces. If you see all forces,
all of them.
all things, okay? Most of the time, it's going to be focused on one of these, you know. What's happening with the sodium chloride? Oh, the ions are disassociating. What's happening with the water? Oh, it's a polar bond. What's happening with the ions in the water? Well, you have an ion dipole interaction. What's happening with the water? A hydrogen bond. All good? Enough John Madden. Okay. So we talked about liquid water, right? Next one. Gas. Water. What is the difference going to be? So you had draw a picture of liquid water, molecular representation of liquid water with its hydrogen bonding. And now do the same thing but for gaseous water. What is the differences there? Think about it, write it down, show it, see if you can express that thought as a picture. And then we'll talk about it in a minute or two. let's kind of go through. So what is the big difference is going to be between liquid H2O and gas H2O that you draw?
The molecules are more excited.
Are more excited, right? They're moving around more, right? Are they going to be, because they're moving around more, are you going to have more or less or equal number of hydrogen bonds? Less, right? So it's pretty hard to show motion in a picture, right? You could draw like little lines being like, woo. What are those? There's a term for that. There's a term for that. It's like lines that indicate motion in a two-dimensional picture. This is an academic team question. So. All right. Yeah, you can do that. Another way to do it is just less of those bonds. More spread out. If you wanted to do the container method, you can do containers as well. So what's the difference between a liquid and a gas in terms of a container? Pools at the bottom, gases fill up the entire container. Right. So if you wanted to do something like this, something like that, you know. You have a bunch of H2Os at the bottom of a container with some but not all of their hydrogen bonding put out, right? And then this is going to be your liquid. For the gas, it would be something like this. One there, maybe one there, and that's it. You know, less number of hydrogen bonds, fully spread out, pulling all of the container, so on and so forth. Now, bonus round. Now do solid H2O. Now go in the opposite direction. So, just describe to me what you're going for. What's the difference between liquid and solid H2O?
So it's obviously a lot denser, so it's going to want to do hydrogen bonding a lot more. And if it does it consistently, you kind of get a lattice structure.
You got a lattice structure, exactly. So you said more dense.
I was about to say, I don't think water
So
does that.
that's the thing. Water's
Oh,
weird.
that's right, expanding.
Water's weird.
Yeah.
Okay. Most things, whenever they turn into a solid, they become more dense.
Yeah.
Okay. but you said the thing. It makes a crystalline structure, this lattice structure. So I got a little picture here, kind of indicate what's going on. So in water, it's kind of random. Water is kind of tumbling all over itself, right? And because it's tumbling all over itself, some of these are here. They stick around for a while. It may break, sticks around, breaks. They are temporary. Okay, they're constantly being broken. Stick around, keep you close by, and then fall apart. These are solid. They stick around a lot longer. And you want to maximize the number of these bonds. And to do that, it forms this structure, and it leaves this big empty space, which is why ice is less dense, which is why ice floats. Ice does not sink. So, there's that. What do you think lasts longer? These hydrogen bonds in liquid water or gas water? Liquid water lasts longer, right? Yeah.
Is there a way to make ice denser than water?
Have you read Cat's Cradle by Kurt Vonnegut?
No.
Read Cat's Cradle by Kurt Vonnegut. It's a science fiction thing, and Kurt Vonnegut was a scientist, but he's a sci-fi writer as well. It's all about to use his example. You know how you can stack cannonballs up, right?
Yes.
Can you stack them up in different formations using different patterns? Yeah. Yeah, there's actually, like, in the military, there's a whole bunch of different ways to stack cannonballs. There's different patterns you can use to make them more dense, less dense, spread out more.
Yeah.
Same idea here. There's different patterns you can do to have different properties of ice.
Right.
Yeah.
Well, what was his name again?
Kurt Vonnegut.
Also,
Just look at Cat's Cradle, you'll see it.
is the oxygen shown in the water, but like in the ice, is it possible for like the oxygen to fuse with hydrogen?
Yeah. So anyway, you can go through and do that. This is one form of ice.
Okay.
There's other forms. Some other what they call allotopes. It's the same thing but different formation of it. So like an isotope but an allotope. All right. So there's that. All good? All right. Next thing. Gaseous O2. Tell me the bond and the intermolecular forces that are taking place. I will say, Weston, it's been a while since I've read the book. I do know Kurt Vonnegut comes from an age where they're from a different age. You know, I don't know what type of material is in the book.
Last
Other than
century. Okay.
he's
Good to know.
I mean, I'll say this: it's like 50s, 60s.
Oh, okay. So
Think about what type of things are going on in the 50s and 60s
nuclear testing.
politically,
Nuclear testing.
racially.
That's good.
So, I'm not for sure. Again, it's been a long time since I've read it. Anytime I recommend books, I always like to throw out, maybe there's something in there that's offensive. He did write a book called Slaughterhouse-Five, which is about the Holocaust. He himself being Jewish. So it's like, yeah, there's a train car of Jews going to the Holocaust, and then time travel shenanigans start happening. He's a science fiction writer. So, yeah, it's a thing. Hey!
Sorry to interrupt. Do you know if we have cobalt glass?
Cobalt glass?
Yeah, the cobalt blue glass for EM spectrums.
Oh. No. We do have EM boxes for like the gases.
Yeah.
If you want to do those spectrums, that's what I usually do.
Spectrometers.
Spectrometers, yeah. Here's all of them.
Sweet.
As in, yeah. I'll say this, some of these are.
I stole the one from,
Yeah, here's that, I have the boxes back there, and, all of the tubes. I think we have like nitrogen, a lot of some of those,
don't work.
well, you know, hey, look, this is the perfect thing for a pencil to go through, right?
Oh, yeah.
That's exactly what we should do.
Oh, all right.
So, a lot of them are messed up with that.
Thank you.
Yep. Okay, guys. Enough of my science fiction recommendations. What type of bond? O2. It's covalent bond. So what kind? Non-polar. Non-polar covalent. So let's kind of just draw this out real quick. If you drew the Lewis structure, that's kind of what you'll see, right? But now we also need the intermolecular forces. So we need two molecules of this for them to interact. All right, now let's kind of run down the list.
No hydrogen.
Can't do hydrogen bonding. No hydrogen.
No dipole.
We have a dipole?
No.
No dipole. Do we have an ion or a dipole?
No.
No. What's left?
LDF.
LDF. So what does that mean? Tell me a story about what's happening here.
The electrons kind of go to one side a little bit, and so the other side gets a slight positive, and then the other side kind of does similar thing.
There you go. So somehow indicate you could do something like this. Draw a little interaction line, you know, the little dash line, and then over here, write LDF. Just to let them know, like, hey, you know, let whoever's,
This is LDF.
yeah, indicate that you know what's going on here, right? You can do that. Or if, you know, you're not an artist and you're not a graphically minded person, if you want to just write out, you know, what is happening, the electrons, blah, 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 then that's fine as well. So, okay. Sometimes they won't even tell you it. They'll just give you a structure, like this boy. So first off, what type of bonds? Covalent, yes, but it depends, right? This bond that I am circling in red is nonpolar. This bond is polar. Ooh, we got multiple things happening, don't we? Ah, jeez. So, is it ionic though?
No.
You can straight up say no ionic. Metallic? No. So we've taken care of those things. You can say it has.
This one of the polar-ish ones.
So if I drew another one of these guys, if I copy and pasted this down here, is there a way to copy and paste on this thing?
Thank you, Dr. Stubby.
But can we copy? I don't think so. But if I drew, I'm just going to draw one part of it. C. If you have this, now we have two of them. What type of intermolecular forces are going to be at play? More importantly, that's not the question I'm going to be asking. That's the question you'll have to answer to get there. But the question I'm going to ask is this thing solid, liquid, or gas at room temperature?
Yeah.
Probably. No, and it has the things instead of this.
So let's kind of run through this real quick. Let's talk about each of these type of bonds and kind of what they look like. Ionic bonds. So these are your salts, right? Is it solid, liquid, or gas at room temp? Solid, right? In fact, when does it become a liquid? What's its melting
Very,
point?
very hot.
Super, super high, right? Which makes sense because this is the strongest type of bond you got, right? Polar bonds, non-polar bonds, they might be solid. Honestly, they might be liquid, right? Hey, maybe be gas, like oxygen, O2, right? How can you tell if these guys are solid, liquid, or gas at room temp? What type of intermolecular forces do they have? The stronger, if they have a bunch of hydrogen bonding, it's probably liquid. If they have a bunch of, a whole bunch of stuff, like LDF, hydrogen bonding, dipole, a whole bunch of them, it might be solid, if it's big enough, right? So, there's that kind of stuff. But most of the time it's going to be like maybe liquid. If you have enough intermolecular forces. Right? Think about something like CO2. What type of intermolecular forces is this guy going to have?
Dipole.
Yeah, it might have a bit of dipole action going on, right?
Yeah.
But what is CO2 at room temp?
Yeah.
Gas, right? So, yeah, just dipole, gas, right? What does this guy have?
Got everything. Like.
It's got a dipole,
Yeah.
right?
It has hydrogen bond because you can attach the oxygen to the hydrogen.
Now remember with hydrogen bonding, you need a hydrogen bonded to FON, one of those guys, interacting with FON.
There's no, all the hydrogen
Oh,
with
okay.
carbon.
You see-
It's definitely gas for room temperature.
Could be like,
Well, you have the dipole, no ions, right?
No ions, so the only one would be LDF.
Then we have some LDFs as well. In fact, we got this entire thing is LDF.
yeah.
This entire thing is LDF, right?
Yeah.
Do we have the ability for this
Not really.
to interact with anything? Is this going to be positive or negative?
Negative.
It's going to be negative, right? It's going to have that slight negative charge, right?
So it'd be.
Could this slight positive charge interact with this guy? Yeah. If you have negatives and positives, they could interact as long as they can reach each other, right? So that's a possibility. Same thing over here. So we have 1 dipole, 2 dipole, 3 dipole, and 6 LDFs. What do you think? Solid, liquid, or gas? Liquid.
Yeah.
Another thing you think of, remember acetone from yesterday?
Yeah.
What did that look like?
Oh.
Ooh. Geez, I don't know, that was yesterday.
No, I remember.
There's acetone.
Yeah.
Comparing this and this monstrosity, now that I've marked it all up,
That's pretty.
which one do you think is going to have a higher melting point? Which one has
That was.
this guy?
Because it just has more.
It's got more stuff, more forces available to it, right?
What is that? Is that an actual?
It's an ester. It's organic chemistry.
Okay. It said Esther. I was like, I know.
You know, ester. Anyway.
You know.
Alright. We good? Like, no?
I don't understand how you, we're expected to do any of this ourselves. I'm too stupid to think about this.
Nah. So, it's, think about this. Let me ask you this. Which one of these has more intermolecular forces?
The big one.
The big one, right? There you go. That one's going to be have a higher melting point. It's going to be harder to break apart. It's going to be more likely to be a liquid. We're going to have to heat it up more for it to become a gas. It'll turn into a solid before the other one. Does that kind of make sense?
Yeah, I meant like, I couldn't get to any of it myself. Like, yeah.
Alright. Let's go through this stuff. Let's give this a shot. Let's say ammonia. I'll even draw out ammonia for you. What type of bond, or what type of molecule is this? If you looked at this, are there electrons on one side that not are on the other?
Yeah.
So it's polar, right? No. Yeah, polar. Right? There's more electrons on this side, right?
Yeah.
So there is going to be a dipole, right? Each of these are going to have a dipole going this way, right?
There's also
So if I had multiple of these, what type of force would it be? Dipole. You get that? So if I compared this to this, which one's going to turn to a liquid first? The one with more forces. You getting it?
Would there also be hydrogen? I just saw N and hydrogen and I was like, hydrogen. Ethyl and my memory.
Bomb.
Is there a way to like decrease the time or the temperature inside a liquid? It's like you only have solid or gas, or is it like a concentration?
We'll talk about that next week.
I was going for the first two parts and I forgot how to leave.
1/10 is the point where there's all knowledge needed.
Review notes. Review notes.